Okay, welcome back. Now I want to zoom in on the question that I mentioned at the beginning of the talk and try to fill in some of the details, right? So the first part, and I already said how I'm going to make a random curve, but I just want to emphasize that there are actually many ways to do it, and this is just one of them. And so that's the thing that I described, which is you take n random points just uniformly in the cube, and you join them together in order. So let's say this is the first point, second point, third point, and so on. And then join the last point back to the first one, right? And then the question that I want to answer is, what is the least area of an orientable surface filling in such a curve? Usually, right? So this is a random situation, so sometimes you'll get a wildly different answer. And one of the things I want to explain actually is, why is there a usually at all? And then, of course, the word orientable, I should tell you what this means. The word surface and the words filling in, I'm not going to explain formally, but just remember this picture that we had in the other video of a surface filling in this curve. Okay, so several comments, and first of all, what do I mean by orientable? That's important. Orientable means it has two different sides. So if you're a person standing on the surface, maybe a blue person, and you're standing on this side, you can't, if you're walking around and you walk all over it, and then you come back to where you were originally, you'll still be on the same side. So this is another example of an orientable surface. If you start walking and you walk all the way around, you'll end up on the same side. Like this. Whereas here's an example of a non-orientable surface. If I stand here and I start walking around, well, everything is fine until the twist. And then once it's twisted around, then I'm standing on the other side. So you should think of that as the surface only has one side, or like you can't tell which side is up and which side is down. And so why am I emphasizing this? Because it makes a difference. So if you take the boundary of this surface, so go this, like this, and then like this, right? That's one curve. And if you want to fill it in with a non-orientable surface, then, right, it's this pretty small area surface. But if you want to fill it with an orientable surface, then you have to fill the whole top and the whole bottom. And so the filling area will be much bigger. So it turns out if you ask the same question for a non-orientable surface, the answer is not going to be very interesting. So that's why I want it to be orientable here. Well, that's not the only reason. Also, for sort of advanced math reasons, it turns out that you really want to think about orientable surfaces. Yeah, so what this is saying is this caveat of the surface being orientable really matters. The second thing I want to describe is, why should there be a usually, right? Because like here, these points happen to land far away from each other, and so you get a pretty big surface, but it could be that they all land right next to each other or just like in a line, and so the surface, the curve looks like this, and then that's going to have a pretty small filling, right? So this is small filling area. And sort of what I want to argue is that things are gonna average out in the end, right? And this is much easier to see with a random process that's simpler, like flipping coins. So, right here, if I only have 8 points, then it's actually not that unlikely that you get this very small area. But as you take more and more points, things balance out. And so with coin flips, right, if you flip twice, then you get a 1/4 chance of heads, right? This is 100% heads. If you flip 100 times, then you have a 1/2 chance of 100 heads, right? Or even like, even if you get 60 heads out of 100, you still start wondering if your coin is fair. And as you flip more and more coins, right, the number of heads, the proportion of heads, so the number of heads over the number of flips is basically always going to go to 1/2. This is the so-called law of large numbers. And it turns out, and it's not obvious, but the same thing is going to happen here, right? As you take more and more points, the area that you get most of the time is going to converge to basically the same thing. Okay, so one last comment I want to make is just to get your gears running, what sort of answer should we expect to get, right? So I told you the real answer is square root of n log n. What really simple heuristics are there? Well, okay. One heuristic is it should be at most c times n. Why? Well, right, here's my cube. And basically the hardest to fill surface that I can imagine is you just go around the perimeter again and again. Right, and so every vertex is at a corner. So this is, if this is n vertices, then the filling area, right, every square has 4 vertices, and there are about n/4 of these squares, and each of the squares has area 1. So this is about n/4. So this is the worst thing that could possibly happen, is you get n over 4. What about the best thing that could possibly happen? So this is a little bit more complicated, but I'm going to argue that the best thing that can happen is c times some constant times square root of n. So in both cases, c is just some constant. So why is this? Here, maybe so I want to say, okay, the lower bound is going to be, right, you sort of, for every strand, you have to match it to some other strand. So what if we could just match every point on the strand to a point on the closest other strand? Right, so that's the best we could do. Right, and now if we manage to do that, what would the area of that surface be? Well, okay, right, the length of the curve is n. So then we'd get n times the length of the curve times the average distance to the closest strand. I guess the length of the curve isn't exactly n, but there's some average length of an edge. And again, law of large numbers, for a big N, it's going to be roughly, the length of the curve is going to be roughly n times the length of the average edge. So there's again some constant c hiding in there. And okay, so then what is the average distance to the closest strand? Well, the easiest way to see this is to imagine sort of right, imagine here's my strand and I grow a tube around it, right? And if the tube has right, if the tube fills up every point of the cube, once on average, right, then the thickness is roughly the distance to the closest other strand. And so right, okay, so this condition says the total volume of the tube is about n, or sorry, is about 1. Right, so And this one, this is the length of the curve times the area of the tube. So the radius squared, right? And so that means that the radius of the tube is going to be about 1 over square root of n. Again, this is hiding some constant, right? It's some constant over the square root of n. And so that means that, right, this here, this is constant times n times a constant over root n. So that is a constant times square root of n. And okay, so this is some wishy-washy lower bound. Hopefully I convinced you that the real answer really shouldn't be any smaller than that. And it turns out it's a little bigger. So, so remember, the answer is, again, a constant times square root of n log n. So in the last installment, I'll tell you a bit about why that is.